So let's go and see an example. How can we like handle these things? So this example tells you we have steam power plant operating on the ideal regenerative cycle. Okay, so here is telling you that we are using regenerative cycle. With one open feed water heater. So again, this one is telling you we have open feed water heater we have here in this cycle. Steam enters the turbine at 15 megapascal and 600 degrees Celsius. What of this point? Point 1, 2, 3, 4, 5, 6, 7. What is this? What is the point that represents this condition? The condition that enters the turbine. Anyone can answer it? What is the point that represents the inlet to the turbine? Five? This one, yes. Yeah, so this is the point. This is the inlet to the turbine. This is correct. So this condition, so this point at 15 megapascal and this point at 600 degrees Celsius. Then, and it's condensed in the condenser at pressure of 10 kilopascal. So this 10 kilopascal, the pressure at which points? What are the paths that representing the heat rejection at the condenser? Yep, 7 and 1. So here we have 7 and 1. This path is at 10 kilopascal. Some steam leaves the turbine at pressure of 1.2 megapascal and enters the open feed water heater. So what is the point that representing the steam or the part of the steam that is, we are taking it from the turbine and introducing it to the feed water heater. So which point is this one? Six, exactly. So this is the point here we have. So this point is at 1.2 megapascal. Okay. So now this is the information we have. We need to find the amount of Y and we need to find the thermal efficiency of the cycle. Okay. So if we're gonna solve this one here, so again, what we are trying to do is to find thermal efficiency. So we have the thermal efficiency is 1 minus Q out over Q in. And Q out okay, well, let's start with the easiest one. We have Q in, this is enthalpy at 0.5 minus enthalpy at 0.4. And we have Q out, this is 1 minus Y, enthalpy at 0.7 minus enthalpy at 0.1. And we know that's Y, this is the enthalpy at 0.3 minus enthalpy at 0.2 divided by enthalpy at 0.6 minus enthalpy at 0.2. So this is what we need to find. So we need to find at the end the thermal efficiency. So we need Q in, we need Q out. This is the equation of Q in, equation of Q out. We have U, the amount of steam extracted from the turbine, which is Y, and we have this equation to find. So we need to find like all these H values we have here. So, and if we need to start this one, so again, we will start regular with what we have. We will start with state 1. State 1, this one is saturated liquid. This saturated liquid at 10 kilopascal. So what we will have at this point, we can go to the appendix, and from the appendix we can say enthalpy at this point is 191.81 kilojoule per kilogram. And also we can find specific volume at this point, which is 0.001 meter cube per kilogram. Then from point 1 we will go to point 2. So let's say state 2. This point is compressed liquid at 1.2 megapascal. So we have H2 minus H1. This will be V1 P2 minus P1, and this is equivalent to the amount of the work added to this pump. And substitute in this equation, then enthalpy at point 2 minus enthalpy at point 1 equal the specific volume, pressure at point 2, 1200, to convert it to kilopascal, minus 10. Then we can say H2 enthalpy at this point will be 193.01 kilojoule per kilogram. And always remember, so this one is in kilopascal. So this is H2. Then we will go to point number 3, state 3. Three is saturated liquid at 1.2 megapascal. Then from the appendix, I can find H3 directly. That will be 798.33 kilojoule per kilogram. And since 3 is inlet to the pump, so at this point also find specific volume at point number 3. So the specific volume at this point will be 0.00138 meter cube per kilogram. Then we can go to state 4. State 4 is compressed liquid at 15 megapascal. So again, 3, 4, this is pump number 2. So we have one equation for the pump. So this means work of the pump 2. This will be H4 minus H3. This will be V3 P4 minus P3. So this means H4 minus H3, 798.38 equal 0.00138, 15 thousandths minus 12 hundredths. So substitute in this equation and you can find specific enthalpy at point number 4. That will be 814.03. And again, just note this, these pressure values are in kilopascal in order to have kilojoule. Okay. So now we have H1, we have H2, we have H3, we have H4, so we can still have 3 more points, 5, 6, 7. So we can go to point number 5, state 5. Superheated steam. At 15 megapascal and 600 Celsius. So at this point we can find H5. So H5, this one will be 3583.1 kilojoule per kilogram. And since 5, 6, 7, all this pass is isentropic, so the entropy at point 5, this will be the entropy at 6, this will be the entropy at 7, so we need to find the specific entropy at this point as well to use it for the other points. So entropy at point number 5, this will be 6.6796 kilojoule per kilogram Kelvin. So now we can go to state 6. State 6, this is still superheated vapor. But the pressure is 1.2 megapascal. We don't know the temperature. We don't know anything about these points, but we know the entropy. Because entropy at point 6, this is the entropy at point number 5. So we know that, and the entropy at point 6, this is equivalent to the entropy at point 5, which is 6.6796 kilojoule per kilogram Kelvin. So we know 2 information at this point. Use to this information, go to the appendix, then we can say from the appendix the value of the enthalpy at this point, point number 6. So this one is 2860.2 kilojoule per kilogram. Also you can find temperature just if needed. To find temperature at point 6, also from the appendix, it will be 218.4 degrees Celsius. Then the last point we have, state 7. It's a mixture of liquid and vapor. So this point is mixture of liquid and vapor at 10 kilopascal. Okay. So again, this is a mixture, so we need to find Q, the fraction of the steam you have. So what we will do, if you remember, so we will start with at 10 kilopascal. So go to the appendix, find specific enthalpy and specific entropy of saturated liquid at 10 kilopascal, which likely we have it point number 1. Point number 1, this is saturated liquid at 10 kilopascal. So HL and entropy at point SL, which is saturated liquid and 10 kilopascal. So luckily this one here will be same as point 1. So we need to, you don't need to like go and find these values again. And find enthalpy of saturated vapor and entropy of saturated vapor at 10 kilopascal. So once you find these values, then you will go to find Okay, to find Q at point 7. So this one will be the enthalpy at point 7 minus enthalpy of liquids divided by enthalpy of vapor, entropy of vapor minus entropy of liquid. So if you, S of 7, this is equivalent to S of 5. So we have entropy at 7, this is entropy at 6 or entropy at 5. Entropy at liquids, so this one is entropy at point number 1. This one, vapor, you can find from the appendix, so you can substitute in these values in order to find X. Let me put the numbers here. So what you will have is 6.6796 minus 0.6492 over 7.4996. So the Q we have here is 0.8041. And then we will use this information to find enthalpy at point number 7. So this will be enthalpy of liquid plus Q, enthalpy of vapor minus enthalpy of liquids. So this will be 191.81 plus 0.8041, and this delta H will be 2392.1. So the result, final result we have, it will be 2115.3 kilojoule per kilogram. So now we have all the enthalpy values we need. Okay. So in order to find, again, the thermal efficiency, so we need to find Y. So Y, this is the fraction of the fluid coming to the turbine that will be extracted and go to the open feed water heater. So this will be enthalpy at point 3 minus enthalpy at point 2 divided by enthalpy at point 6 minus enthalpy at point 2. So if we substitute all the values here, we have Y will be 0.227. And by the way, this is the first requirement that we need to find in this problem. So this problem, the first thing is to find Y, the amount of the working fluid that we extract from the turbine and introduce to the feed water heater. Then once you find Y, then you can find the other Q inlets and Q outlet. So we have Q in, this one is H5 minus H4. We have all these values, all the enthalpy values given, so Q in, this will be 2769.1 kilojoule per kilogram. And similarly, you can find Q out, which is 1 minus Y, H7 minus H1, so this one is 1486.9 kilojoule per kilogram. Then we can say thermal efficiency, it's 1 minus Q out over Q in. So if you put all the numbers we have right now, so the thermal efficiency of this cycle will be 0.463, or percent, it will be 46.3%. And this is the second requirement that we need to find. Is it clear? So again, so the steps may seem longer steps. You need to use the appendix a lot in these type of examples, but the solution itself is very systematic. So we start at one point and then we continue. If you have a path on the pump, so you have a certain equation you can use. If you have the side of the turbine and these things, the isentropic expansion, so you can rely on the this point have the constant entropy. If you have point at the two-phase region in which we have mixture of liquid and vapor, so you keep in mind that we need to find Q. So Q is the key to find the solution. And for this regenerative, we have another term, it's Y, which is the fraction of steam extracted from the turbine, because we will need it to find Q out, that we will need to find the thermal efficiency.